Hello everyone, I'm Carlene Pilar Arceo, and I hope you're up for a quick walk down memory lane for a bit of Euclidean geometry, then a leisurely stroll forward to the modern geometries. We all studied geometry in high school. We all know about parallel lines and the sum of the angles of a triangle. We have all learned about Euclid's The Elements and the first 5 postulates. We called it geometry. Today, we will give it a more specific name, and you will see in a while why it's necessary to do so. I mentioned The Elements, written by Euclid around the 3rd century BC. Can you remember what kind of a book it is? Or is it even a book? If you recall correctly, then yes, it's not just one book, but a set of 13 books like an entire encyclopedia. Did everything in The Elements, all the postulates, all 465 theorems, and their proofs really originate from Euclid? If you recall correctly again, then no, not at all. But his great work as author was the putting together of all the mathematical knowledge during his time, not just geometry, but even number theory and algebra, among others. The works of Pythagoras, Hippocrates, Eudoxus, and many more Greek mathematicians. Euclid organized everything into a smooth, flowing whole, replete with explanations and proofs. It was not just a matter of compiling the works of Pythagoras into one book, the works of Hippocrates in another book, and so on. Rather, he worked through all of them and reworked them so that they would fit together and progress according to elegant logic. This logic would become known as the axiomatic approach, following deductive reasoning. This is a major Greek contribution beginning from the time of Thales to mathematics, so that mathematics and its subfields would be referred to as axiomatic systems. Sa madaling salita, may sinusundan silang mahigpit na mga panuntunan na pinangungunahan ng mga axioms at postulates, kung saan nakabase ang lahat ng mga kasunod na deklarasyon o teorema. Kung matatandaan, ang mga axioms at postulates, ang mga deklarasyon na tinatanggap bilang katotohanan ng walang kinakailangang paliwanag o pagpapatunay o self-evident truths, statements accepted as true without need for proof. Kung matatandaan din, hindi ba nung high school, isa sa mga ginawa natin ay ang pagbuo ng tinatawag na geometric proofs? Ito yung mga 2-column proofs, kung saan ang unang column ang maglalaman ng statement at ang ikalawang column ang maglalaman ng kanyang karampatang dahilan o reason. Naalala niyo ba yan? Sa puntong ito ay magandang alalahanin natin ang ilang piling postulates. Let's recall the first 5 postulates of Euclid. As the first of many in an axiomatic system, it is implied that these are the most basic and the strongest of the statements in the system, in that everything that follows could be traced back to one or some of them as part of their basis. If you remember these first 5 postulates, then please state them along with me. Postulate number 1. A straight line can be drawn joining any 2 points. Postulate number 2. Any straight line can be extended indefinitely in both directions. Postulate number 3. Given any point and any distance, a circle can be drawn. Postulate number 4. All right angles are congruent. And postulate number 5. If 2 lines are drawn which intersect a third, in such a way that the sum of the inner angles on one side is less than 2 right angles, then the 2 lines, if extended far enough, must intersect each other on that side. These are self-evident truths. These are true statements not needing any proof or explanation. Take a look at each one, and in your minds, affirm that they indeed settle in your minds as immediate truths. Kumusta? Upon reviewing them, did you find all of them okay? Or was there a postulate which you may have had difficulty with, absorbing, and accepting without further explanation? If there was one, which was it? Kung papipiliin kayo ng isang postulate na maaring hindi ganoon kabilis at kaagad-agad ang hulog, alin ito sa 5? Alin ang kinailangan nyo pang basahin ulit dahil nag-iwan ito sa inyo ng pagtatanong o pagtataka kung hindi man ng pagdududa? At kung may napili na kayo, maaari ko ba itong hulaan? Susubukan ko, ha? Ito ba ay ang ika-5? Did you think that the 5th postulate was the one that's not like the others? Then welcome to the club. You are not alone in thinking about, looking at, and reading twice or more Euclid's 5th postulate. For starters, it has more words than the first 4 postulates strung together. Did you know that for some time, mathematicians even speculated that the 5th postulate was a theorem and tried proving it using the first 4? This prospect ended in vain. Still not satisfied with their drilling of the 5th, some mathematicians later endeavored to speculate. What if it was false? Surprisingly, this avenue gained some success in the 19th century. Picture it. The postulates came out in the Elements in around 300 BC. The pivotal outcome from assuming it was false emerged in the early 1800s AD. For more than 2,000 years, the 5th was put under the microscope by generations of mathematicians. Equivalent rewordings, whether intentional or not, were done by Proclus in the 5th century, Wallis and Zachary in the 17th century, Lambert, Legendre, and Playfair in the 18th century. In 1767, D'Alembert even called this whirlpool around the 5th the scandal of elementary geometry. Finally, some concrete progress was made in the 19th century by Carl Friedrich Gauss, Janusz Bolyai, and Nikolai Lobachevsky. Over the period 1817 to 1829, the 3 geometers labored over the same question as those who came centuries before them. What shall we make of the 5th postulate? What happens if we assume it is false? Independent of each other, Gauss in Germany, Bolyai in Hungary, Lobachevsky in Russia, the trio came up with what would be known as the first non-Euclidean geometry, hyperbolic geometry. This is why the geometry of Euclid and his Greek colleagues would henceforth be known specifically as Euclidean geometry. To explain this in more detail, I will use Playfair's version of Euclid's 5th postulate. Recall, too, that the 5th is also known as the parallel postulate, though upon reading it, the take on parallelism may not be immediately evident. It is directly referred to, however, in Playfair's version, and I guess you remember his version much better than Euclid's. Playfair's action. Given a line and a point not on it, exactly one line can be drawn through the point parallel to the given line. It is much easier to falsify this version than the original. Let's see if you can think like Gauss, Bolyai, and Lobachevsky. Give a statement that renders Playfair's action false. In other words, find a contradiction. Sige nga, mag-isip kayo ng isang pangungusap na magsisilbing kontradiksyon sa action ni Playfair na nagsasabing bukod tanging isang linya lamang ang pwedeng dumaan sa isang tuldok nang hindi sasalubong sa isang linyang hindi kinabibilangan ng tuldok. Bukod tanging isang linya lamang. Yan ha, binigyan ko na ng diin para matumbok ninyo. Nakuha niyo ba? Pag sinabing bukod tanging isa lamang, ano ang agarang pumapasok sa isip ninyo na pangontra? Tama. Paano kung hindi lang isa? Sigurado ka ba na iisa? Paano kung may isa pa o dalawa pa O higit pa? Indeed, this is the first contradiction to the fifth, and it reads, given a line and a point not on it, more than one line can be drawn through the given point parallel to the given line. Lobachevsky even directly says that there exist two lines parallel to a given line through a given point not on the line. So let's look at the model of Playfair's axiom, and to falsify it and to illustrate the Lobachevskian version, let's try to draw a second line through the given point parallel to the given line not containing the point. If I keep the line straight, then Euclid would be correct and I will surely intersect the given line. However, if you really want to avoid an intersection, what does your logic and intuition tell you? Yes, veer away from the given line. But how could this happen? Think further. What else does your logic and intuition tell you? Yes, that the only way a second line could be realized is if it were a curve, so that it could smoothly curve away from the given line and satisfy the still standing definition of parallel lines, that they shall not intersect. Arcs that curve away from each other, what do these remind you of? Hyperbolas. And so, the new geometry is called hyperbolic geometry. For emphasis, here's a model that shows even more than two such lines satisfying the first contradiction. It's known as the disk model, which Poincaré created in the late 1800s. Here we can clearly see many lines or arcs drawn through P, parallel to, that is not meeting and simply curving away from the line L. Thus, lines in hyperbolic geometry, or hyperbolic lines, are actually circular arcs whose ends are perpendicular to the boundary of the disk. And the disk's boundary, take note, actually doesn't exist. This is to ensure that the second Euclidean postulate still holds, that a line can be extended indefinitely in both directions. In fact, in non-Euclidean geometries, the first four Euclidean postulates all hold. It is only the fifth which will have a different version. Did you pick up on my segue? I said non-Euclidean geometries in the plural. O meron pa palang iba? Oo, may isa pa. Isa pang non-Euclidean geometry. Ibig sabihin, may isa pang pwedeng contradiction sa axiom ni Playfair. So, balikan na naman natin. Playfair's axiom. Given a line and a point not on it, exactly one line can be drawn through the given point parallel to the given line. At ito ulit ang unang contradiction. Given a line and a point not on it, more than one line can be drawn through the given point parallel to the given line. In effect, we are looking for what is left among the cases for Playfair's axiom. We have accounted for exactly one and more than one, so it should be clear what the last case would be. Less than one or none. So we state it formally as follows. Contradiction number 2. Given a line and a point not on it, no line can be drawn through the given point parallel to the given line. This is the second contradiction, and it leads us to the second non-Euclidean geometry, elliptic or spherical geometry. Before I give more details about elliptic geometry, let's take a moment to take note of the wonderfully simple logic that just went on. The original version says there's exactly one. Contradiction number 1 says there's more than one. And then contradiction number 2 says there is none. To contradict or falsify, one angle, the more immediate one in my experience, is that there could be more than one such line. Then if one backtracks and looks at the original as an existence axiom, saying that one such line can be found, then the other angle becomes equally immediate. Are you sure that even one can be found? What if no such line exists? This second angle of contradiction was taken by German mathematician Bernhard Riemann, a student of Gauss in the mid-1800s. So sometimes, elliptic or spherical geometry is referred to as Riemannian geometry. Here's the model, which of course is a sphere. The lines in this geometry are again curves. In particular, they are great circles, or circles on the sphere with the same diameter as the sphere. And note that in this geometry, there are effectively no parallel lines. This means that all lines will meet. If we look again at the model for Playfair's action, even the very first line drawn through the given point should intersect the given line. Same with all succeeding lines drawn through that point. This will happen for all points and lines in the geometry if indeed their milieu is a sphere. In fact, spherical lines, as intersecting great circles, will always intersect each other, not just once, but twice. So perhaps the question on your mind now is, what good do these non-Euclidean geometries do? Hyperbolic geometry makes beautiful art and hardcore science, like the theory of relativity. Also, the lens of the human eye is hyperbolic. Elliptic geometry is used for navigation by airplane pilots, ship captains, for map making, projections, GPS, among others. How useful and appropriate these surprise non-Euclidean geometries turned out to be. Now let's move on to another modern geometry. This will be our third, projective geometry. In name and theory, you will probably think it is unfamiliar to you, but the name itself should lend to some intuition about the geometry. Projective. What comes to mind when you hear the verb project? It usually refers to putting something forward beyond the source, like your voice. Sa Filipino, ito yung pagbato ng boses. Or forecasting an event given source data. Or casting an image, like a shadow. Or even exhibiting a quality which an individual may not necessarily possess, like projecting confidence or cheer. In geometric figures, this is how projection looks. It is the creation of an image based on an original, which is viewed from a certain perspective, or point of perspectivity. The image is created by projecting its points along projective lines that emanate from a point of perspectivity, and connecting the points again according to the original image. If the point of perspectivity were a light source, like the sun or a light bulb, then if an object were placed under it, an immediate projective image would be the shadow it will cast on a surface, like the wall, or the floor, or the ground. You have met this geometry before in your drafting classes, where you drew different three-dimensional objects realistically using perspectives. You remember drawing a cube like this? We all know that the sides of the cube in real life are parallel to each other. However, in real life also, depending on where you stand, opposite sides don't actually seem parallel at all. The far ends seem to narrow towards each other. Just like the sides of a road, they are surely constructed parallel to each other. Yet when we look at them and navigate them far ahead of us, they seem to approach each other. As far as we know and can reach, these parallel sides cannot meet. But how would they behave when they are too far away that we can no longer reach or see? Could they really meet, as they seem to? What appears to be a meeting point in the horizon for parallel lines is known in the visual arts as the vanishing point. It makes artwork, photographs, and the like realistic because it gives a two-dimensional rendition of a three-dimensional space, the requisite depth. Look at these two paintings. The one on the left was obviously done without the benefit of a vanishing point. The one on the right already benefits from it. Can you spot the vanishing point? Look at this painting. The use of perspectivity and the vanishing point shows depth. You can distinguish easily the images which are near the viewer and those which are far. Then look at these photographs. It's as if you can really feel how long the corridor or tunnel is or how tall a building is. So where does this bring us in terms of our new geometry, projective, and how is it related to Euclidean geometry? For sure, it contradicts one pillar principle of the latter, that parallel lines should never meet. In projective geometry, parallel lines exist and they will meet somewhere in the far, far distance where we can neither reach nor see. In mathematical terms, where is this place? Then we can neither reach nor see. Any guess? Correct. Infinity. Therefore, in projective geometry, parallel lines will meet at some point at infinity. This is very different from parallel lines not existing. That's in elliptic geometry. In projective geometry, parallel lines will exist and they will meet at a point at infinity. Point at infinity. That is the real name of what you called in drafting and practical arts as the center of perspectivity, and what is called in art as the vanishing point. Here is a projective model of parallel lines meeting at a point at infinity. It is called a pencil. I guess the figure explains quite clearly why it was named so. Here's another illustration to help you get the picture. And just to emphasize that Euclid's postulates still hold, the points at infinity will still form a line. This line will only contain points at infinity. Mahiwaga ba? Ngunit tila napakatotoo din. Ang husay, no? May isa pa akong gustong ibahagi sa inyo. For this modern geometry, the fourth and last one for this lecture, the name itself will immediately tell you how it differs from Euclidean geometry. Finite geometry. Imagine a system with only a finite number of points and lines. Of course, we also expect only a few actions. Doesn't it make you wonder? One big benefit of having just a few elements is the quick visibility. The logic, following the axioms, and validating the theorems is accessible. Model construction is fun and easily done. Let's do some examples. The first one is three-point geometry. Its axioms are: first, there exist exactly three distinct points in the geometry. Second, not all points of the geometry are on the same line. Third, two distinct points are on exactly one line. And what is our model? A triangle. Since the figure was built from the axioms, any further observations will be due to the axioms, so that the corresponding claims and observations will take the form of theorems. For our current geometry, three-point geometry, we see that each pair of lines will intersect once, and that there are a total of 3 lines. These are precisely the theorems. Theorem 1, 2 distinct lines are on exactly 1 point. And Theorem 2, the three-point geometry has exactly 3 lines. And that's it for the finite geometry of 3 points. Wasn't that neat? Let's have some more fun. Here is 4-point geometry. Axiom number 1. There exist exactly 4 points. Axiom number 2. Each 2 distinct points have exactly 1 line that contains both of them. Axiom number 3. Each line is on exactly 2 points. Constructing the model axiom by axiom is a wonderful exercise in logic and following instructions, much like playing a game of drawing and following the rules of the drawing game. Now try your hand at drawing further conclusions, thereby forming the theorems yourselves. Did you also conclude these 2? 4-point geometry has exactly 6 lines. and each point of the geometry has exactly 3 lines on it. Very good. Now that you got the hang of it, I will let you do on your own 4-line geometry. Axiom number 1, there exist exactly 4 lines. Axiom number 2, any 2 distinct lines have exactly 1 point on both of them. And axiom number 3, each point is on exactly 2 lines. Do you have the model? Can you guess the theorems? If you drew your model properly, you should get the following. There exist exactly 6 points, and each line has exactly 3 points on it. Excellent! Aren't the modern geometries fun? Just 20 minutes ago, you knew just one geometry, Euclidean geometry. Now you know a total of 5, Euclidean, hyperbolic, elliptic, projective, and finite. Remember also that the latter 4, the new ones you learned just today, are called the modern geometries. It is thus only fitting for geometry to have a modern definition. And it is the study of sets of points, their properties, and their relations. Now, if you're asking, could all of them be true at the same time? Or is one of them more true or less true than the others? Allow me to quote Poincaré. One geometry cannot be more true than another. It can only be more convenient. So if someone asks you about parallels or the sum of the angles of a triangle, you can impressively counter with, in which geometry? Well done, dear audience. Thank you very much for listening and for joining me in this introduction to the modern geometries. I hope you had as much fun as I did. Thank you.